So I'm not sure if everyone's aware, but cardiovascular disease is the #1 cause of death in the United States. And within the past few years, the rate of deaths due to cardiovascular disease is beginning to decline. However, the burden of cardiovascular disease still remains on our country and most of the world. And because of this, there's still a need for improved technological developments that could improve therapeutic procedures and also assess staging of disease. One of these technological advances is the development of catheter-based technologies to replace open heart surgeries. Some examples of these could include implanting stents to open up coronary arteries, or taking biopsies of the heart muscle to assess if a patient has a rejection after they received a heart transplant. And if you could imagine, as we're moving from open heart procedures to catheter-based procedures, the physician no longer has a view of the heart while they're conducting their therapy. So the catheter-based procedure that my lab is interested in is called radiofrequency ablation therapy. And in this technology, we're inserting flexible catheters into the heart chambers. The first procedure is to detect areas that are producing abnormal electrical signals. Once that area is detected, electrical energy is delivered to treat the arrhythmia, and through the deposition of energy to the tissue, the patient is cured of their arrhythmia, restoring a normal heart rhythm. Here are some example images of the electrophysiology or EP laboratory while they're conducting a radiofrequency ablation procedure. And each of them shows various critical steps. So the first includes a physician in the control room looking at real-time measurements. The second includes a physician with a nurse that's at the bedside of the patient as they're inserting the catheters into the patient's heart. And the third is real-time X-ray view of the chest. And what we could see within the first image are a wide variety of measurements that are taken from the tips of the catheters. These could include the tissue temperature, the tissue resistance or impedance, in addition to the power that's being delivered to the tissue. And this information is not only available to the physician in the control room, but also the physicians and nurses who are at the bedside within the surgical suite. And they use those measurements in addition to the real-time X-ray as a way to guide the procedure. And so first, with their X-ray, they could see the catheters, and they use that to guide the placement of the catheter in the appropriate chamber in the heart. And once it's at the right location, you deliver energy and use the real-time measurements of power, temperature, and impedance to determine if the procedure is efficacious. And so as you could see, the use of X-ray is extremely important in this procedure. And what we could see within these X-ray images are the catheters, but we actually don't see the heart. And so my work is to provide a view for the physician of the heart while they're conducting this procedure. And so in the future, we have this vision that while they're conducting radiofrequency ablation procedures, they have the fluoroscopy, the real-time measurements of power, temperature, and impedance, in addition to optical imaging. So the optical technology that we're using is called optical coherence tomography. It's a tool that's very similar to ultrasound, where we could get cross-sectional images of biological tissue, but because we're using light, we get images on the order of the size of a cell, which is around 10 microns. This is an extremely versatile tool. It could be used to image a wide variety of samples, and here I'm showing a three-dimensional reconstruction of a section of a mouse heart. And so when we're trying to address the challenges of radiofrequency ablation therapy, what we need to do is design an optical catheter to image in real time inside of a beating heart. And one of the challenges of imaging in the heart is the presence of blood. And this is something that has precluded the use of optics for imaging in the heart. And that's because the optical properties of blood limits the light's ability to interrogate the tissue beneath it. And so taking design cues from the radiofrequency ablation catheter, I designed an optical catheter that images while in contact with the tissue. So to demonstrate the utility of this technology, I've shown some time series images obtained with optical coherence tomography catheter. And this is done while we're generating energy into the tissue. And so the first image shows before we're delivering energy, where we have this characteristic dark band that is indicative of normal tissue. And then as we're delivering energy to the tissue, which is heating it, that band decreases, and then by the end of the ablation, it's completely gone. And so here is just one example where we could see real-time dynamics of energy delivery into the tissue, which is now currently not available. And importantly, this technology provided the first real-time imaging of the heart muscle ever. This was actually one of the most exciting experiences as an engineer. And so if you remember, what I mentioned before was that blood limits the light's ability to interrogate the tissue beneath it. And so what you're seeing here is that with OCT, we could directly assess whether our tissue has contact with the catheter. And this is a parameter that's extremely important to the radiofrequency ablation. And so when the catheter is not in contact, the blood absorption and scattering limits the light's penetration depth, and we have a very shallow imaging depth. Whereas once we're in contact with the tissue, the catheter displaces the blood within the field of view, and then we get a nice image of the endocardium. And so from this, we could see that our vision of realizing optical coherence tomography imaging to guide radiofrequency ablation can be utilized. One, we've shown that we could image in the presence of blood in addition to visualizing dynamics. Furthermore, the optical coherence tomography provides very high resolution images of biological tissue. And this is extremely important because with that, we can start to look at the architectural structure of the heart, which directly correlates to the electrical function. Within our laboratory, we're currently pushing forth technology to extract out the three-dimensional structure of the fiber organization of the heart, which correlates to the electrical function and mechanical properties. And so I'd like to thank everyone for listening and also for allowing me to share the vision of my laboratory, which is the Structure Function Imaging Laboratory. And our vision is that one day optical technologies will be the next platform imaging modality within the cardiac electrophysiology laboratory. Thank you.